This is test of the goodness of fit with R square. After the estimation of the parameter like alpha, beta in the two variable linear regression model, and the other parameter is sigma square, and determination of regression line, we need to know how good is the fit of this line to the sample observation of y and x. This is to say that we need to measure the dispersion of observations around the regression line. The measure of goodness of fit is the square of the correlation coefficient, that is R square. R is the correlation coefficient, and if we square, then it is called the square of the correlation coefficient, which shows the percentage of the total variation of the dependent variable that can be explained by the independent variable, that is x. So the total variation is denoted as TV. So the total variation of y is equal to sum of I is equal to 1 to n. Here 1 to n the number of observation. First bracket yi minus y bar is bracket close and then square. So that is equal to small yi square. And in the next line, explain variation, that is sum of I equal to 1 to n y hat minus y bar its square is equal to y hat square, and the unexplained variation it's denoted as uv, it's equal to sum of capital yi minus capital y hat whole square is equal to ei square. So the total variation is equal to explained variation plus unexplained variation. If we divided this TV by TV is equal to EV by TV plus unexplained variation by total variation, then we get it's equal to 1, because total variation divided by total variation is equal to 1, and so the square of the correlation coefficient is equal to explained variation divided by total variation multiplied with 100. So here ei is equal to capital yi minus y hat. So here yi minus y bar plus y bar plus y hat. So here y bar, capital Y bar plus capital Y bar minus capital Y bar cancel out. So ultimately we get yi plus yi minus y bar if we take a bracket. So in the next line, yi minus y bar minus of yi hat minus of y bar, that is equal to small yi. So we know that capital yi minus y bar equal to small yi, capital Y hat minus y bar equal to small y hat, and if we interchange, then we get small yi is equal to ei plus yi hat, that is equal to sum of yi hat sum of small yi square is equal to, take summation both side, we get sum of ei plus yi hat whole square. So sum of small yi hat yi square is equal to this is a plus b square formula, we apply this, a square plus b square plus 2ab, that means sum of ei square plus sum of ei hat square plus 2 into sum of ei yi hat, it's equal to sum of yi square is equal to sum of ei square plus sum of ei hat square. So the last term, that is 2 sum of ei yi hat, it's equal to 0. We get the solution here. I represent at this part ei yi. So before going to this proof, first mention that yi hat equal to alpha hat plus beta hat xi, yi bar equal to alpha hat plus beta hat xi bar, yi hat is equal to yi hat minus y bar. So we know yi hat and yi bar, alpha hat plus beta hat xi minus alpha hat minus beta hat x bar. So alpha hat cancel out. So alpha hat cancel out, and if we take common beta hat, then get capital xi minus x bar bracket and beta hat common. So beta hat into small xi, because we know that xi minus x bar equal to small xi. So ultimately yi hat equal to yi square is equal to beta hat square xi square, and beta hat is equal to xi into yi divided by xi square. From where we get beta hat is equal to sum of xi yi divided by xi square. So here I can show that ultimately so we can show in this way, because if we cancel out sum of xi, then we get ultimately yi divided by xi. This term finally we get. So sum of ei yi hat is equal to 0. That means beta hat, sum of beta hat xi into small yi minus small yi hat. So ei is equal to yi minus yi hat, and yi hat is equal to, from here, that is from this line, beta hat xi. So if we multiply, then get sum of beta hat xi yi minus beta hat square sum of xi square, and beta hat sum of xi yi minus beta hat sum of xi square, but the other beta hat is equal to sum of xi yi divided by sum of xi square. And here if we cancel out sum of xi square, then finally get at this line that beta hat sum of xi yi minus beta hat sum of xi yi. So cancel out both this term and get ultimately 0. I am not doing here, but the result is 0. So sum of ei yi is equal to 0, and at the next line 1 is equal to sum of yi hat divided by sum of yi square plus ei square divided by sum of yi square. This is like 1 is equal to explained variation divided by total variation plus unexplained variation divided by total variation. at this line we can show in this way. So the r square is equal to equivalent variation by total variation in this way. Sum of yi hat square divided by sum of yi square, it's equal to yi hat square is equal to, we know that, beta hat square sum of xi square from this line divided by sum of yi square is equal to beta hat into sum of xi square divided by sum of yi square. So r square is equal to, we know the value of beta hat, so this term and this term we use from the value beta hat. This is the value of beta hat, and ultimately here also sum of beta xi square sum of xi square cancel out in this way, and ultimately get sum of xi small yi square divided by sum of xi square sum of yi square is equal to r square is equal to, so we know that sum of xi yi divided by xi is equal to beta. One value is considered beta hat and other value it's like same, sum of xi yi divided by sum of yi. Now when explanatory variable are more than one, we consider multiple correlation. The square of the correlation coefficient is called coefficient of multiple correlation coefficient, that is denoted by capital R square. The previous case was the correlation coefficient only two variable, but more than two variable. Here consider multiple correlation coefficient, that is denoted by capital R square. So capital R square consider when two or more explanatory variable, it's defined and explained variable. So that means two or more variable are independent and there is only one dependent variable, that is y, and more than two variable or three or more are considered as independent variable. That is shows that the percentage of the total variation of y explained by the regression plane, that is by change in explanatory variable, that is x1 x2 x3 like that. So capital R square y x1 x2 is equal to sum of small y hat square divided by y square is equal to y hat minus y bar whole square sum of y minus y bar whole square. In the next line, that is equal to beta 1 hat sum of small y x1 plus beta 2 hat. There is two parameter beta 1 beta 2 for x1 x2 explanatory variable, but only one there is a dependent variable and more than one explanatory variable, that is why consider multiple correlation coefficient and divided by sum of y square. So r square is equal to 1 minus r square into n minus 1 divided by n minus k. It's equal to r bar square, that is an adjusted r square. So r square shows the percentage of total variation of y explained by the regression plane, that is by change in the explanatory variable. And the rest of the parts like this part are not consider because this is another part. I will discuss it later.